Swayam Prabha. Digital India. Educated India.
Good morning, students. Welcome to this lecture. In this lecture, we will talk about digital twins. It is just the right time for us to move to this topic because you have learnt about how different sensors work. You have learnt about how these sensor data can be accessed using a web server that you can create yourself. And now we can move on to an advanced concept that uses not one sensor but lots of sensors. Okay, so lots of sensor data integrated on one platform. That is what digital twins are all about. So at the end of today's lecture, you would have understood the concept of digital twins. What are digital twins? Okay, and you would have learnt how to differentiate between digital models, digital shadows and digital twins. So three different types of representations which have different connotations and different use cases: digital models, digital shadows and digital twins. You would have learnt how to create architectures of digital twin systems. You will be yourself able to create the architecture of a digital twin system, take a physical system and create its digital twin. And also at the end of today's lecture, you would have learnt how to derive benefits from using digital twin systems in real world applications. So I'll start with an analogy. Okay, so these are twin sisters. Okay, so you can see they are almost identical. Okay, they were born together and they are the daughters of my younger brother. So one's name is Venus and the other's name is Serena. Okay, from tennis. You see, Venus and Serena Behera. Okay, so they are twin sisters and they are having a good time on Christmas Eve. Okay, so everyone understands what twins are about? Yeah. So this analogy should feed into everything that we learn today. So what is a digital twin? A digital twin is an up-to-date representation of an actual physical asset in operation. Okay, so a digital twin is an up-to-date representation. So key here is this word up-to-date. Up-to-date means it is an exact copy of a physical asset. Okay, whatever is the state of the physical asset, that same state is there in the digital twin. Okay, it is a digital representation on the computer. Okay, but it has the exact same state as the actual physical asset. So it is up to date. Okay. So if the physical asset is sensing 30 degrees Celsius, then on the digital twin that is there on the laptop, that is also updated with that exact sensor value of 30 degrees Celsius. Okay. So it is an up-to-date representation of an actual physical asset which is in operation. Okay, a physical asset that you are currently using on the shop floor, any or engineering firm. Okay, so that physical asset, it's up-to-date representation, instantaneous representation. That is what a digital twin is. So as a representation of an asset in operation, a digital twin reflects the current asset condition and includes relevant historical data about the asset. Okay, so it reflects the current asset condition. What is the state of my asset right now? And it also includes relevant historical data about the asset. So what has happened to this asset in the past? Okay, what has happened to the asset in the past? All of that historical data is also available in that digital twin representation. Okay. So digital twins can be used to evaluate the current condition of the asset. So they can tell you about the current condition of the asset. Okay. So whether it is in a good condition, in a bad condition, it has gone through half of its life, quarter of its life, 3/4 of its life. So, all of that evaluation can be done using the digital twin. Okay. So, current condition of the asset, and more importantly, it can help you predict the future behavior. So, based on the entire asset history, you can tell what will happen to this asset in the future. Okay. And as a result of predicting this future behavior, you can refine, control and optimize its operation. Okay. So, the control of the asset may already be there. You may have some control systems in the asset, but you can refine this control based on the history of the asset, which helps you predict the future behavior. And as a result, you can optimize its operation. Okay. So, because you are able to predict the future behavior based on the current condition, which is instantaneous, you can refine the control and optimize its operation. So, you can make it perform better. Okay, its operation will be optimized. So, you can get the best benefit that you can think of from that asset. Make sense? So, what can a digital twin model? Well, a digital twin is used in many different sectors today, and the digital twinning capabilities are being developed all over the world. Okay, there are lots of people that are working on digital twins. So, a digital twin can model a component, a system of components, or a system of systems. Okay. So, a single component, okay, it can model a single component. Let us say you create a model of the motor that is there inside this electric fan. Okay. So, that is a component. Okay. Or you create a digital twin of the entire fan. Okay. So, that is a system of components. So, the fan has many different components. It has blades, it has motors, it has these shafts, it has a lot of mechanical parts, it has some electronic circuitry, it has some wiring, all of that is the system, right. So, the system of components. Digital twin can capture an entire system of components, or it can capture a system of components, system of systems. So, there are many different fans here, 1, 2, 3, 4, all of these 4 fans together create a system of systems. Okay. So, it can model a system of systems, a component, a system of components, or a system of systems. Okay. So, examples of digital twins are pumps, engines. So, if you create a twin of a pump, you can create a twin of an engine, you can create a twin of a power plant. So, that would be a system of systems, right. A power plant would be a system of systems, many different systems. Okay. Manufacturing lines, those are again systems of systems. Fleet of vehicles, again system of systems. Okay. Engine, that is a system of components. Pump, that is a system of components. Okay. So, a digital twin can create models of many different industrial applications. Okay. An example pump you can see here, triplex pump. This is a fleet of vehicles and this is the power plant. Okay. So, digital twin can model all of these. Okay. So, digital twins, although they can model all of them and create a copy, they are different from conventional modeling. Okay. Digital twins are different from conventional modeling. How? So, in the conventional modeling, you had a physical object and you had a digital object. So, you created a model of the object on your computer, but it was not at all linked to the physical object. There was nothing from the physical object that was going into a digital object. You just created a model of this. Okay. So, example, you have an electro-discharge machining process, you create a material removal rate model on your computer. So, that is a digital model, but that model is not taking in any data from the electro-discharge machining process. Okay. So, what is it? It is just a digital model. Then we have digital shadows. These digital shadows are digital objects that are getting some one-way data from the physical object. Some data from the physical object is entering the digital object and that is creating this digital shadow. Okay. There is one way information flow from the physical object to the digital object. So, that creates a digital shadow. Okay. So, it is a shadow of that physical object and it is getting the data in real time, and based on that this model here is getting updated. You are changing the model parameters with time. Okay. A digital twin not only gets the data from the physical object, but it passes data back. So, there is two-way flow of data. Okay. So, that is a digital twin. So, that is how a digital twin varies from a digital shadow and a digital model. Everyone understands? So, if you yes. So, let us have a look at an example. Okay. Here you can see in the healthcare system, this is a model of some human upper airway geometry. Okay. So, this is the upper airway geometry and it has been modeled, and that model is giving you some simulation results. Okay. So, this model is some finite element model that is created on your computer using some software such as ANSYS. Okay. So, what is that modeling? It is modeling the flow through the human upper airway, and it is helping you plot some graphs and understand the system better. Okay. So, that is a digital model. Now, you can create a patient specific model which is just for this particular patient. Okay. So, if it is for this particular patient, then you can take some data from this patient and insert it into this model, then that becomes a digital shadow. So, for a specific human being, you take some data and you incorporate it into this model, then it becomes a digital shadow. So, that is a patient specific model for fundamental understanding. There is some flow of information from the object to this model. So, that creates the shadow. Now, if we create a twin, then what it will do is it will take this patient data in and it will take this model in and then do the diagnosis based on that dynamically in real time. Okay. So, in the digital twin, you take this patient's face, you analyze this face, and based on that you do some principal components analysis and you come to some conclusions based on that by doing this statistical analysis, but also you have the model of his whole body available on the computer and you analyze that. So, you add the two together and you do your dynamic diagnosis in real time. So, that is the two-way flow. Okay. So, you are taking from the physical object and you are taking from the digital object and then you are doing your diagnosis. Okay. So, that is this is just the model for understanding, but here you are using both the model and the object to do a diagnosis. So, that is when it becomes a digital twin. Okay. Now, this is crucial because many of you are doing practical projects on this course and you can incorporate this digital twin concept into your practical project and it will take it to a new level. Okay. So, why should we use a digital twin? Of course, it is more complex, it is very much individualized, it is customized. So, it is more complex. So, why use this digital twin? The digital twin can enable us to do lots of different new things such as anomaly detection. Is there a problem? Is there a problem in our system? Can we detect it? Okay. Because we have this model that is continuously talking to a physical object, then we should be able to detect anomalies in real time. So, it gives us hard real time control. What we can also do with the digital twin is predictive maintenance. We can predict failure in advance, okay, and therefore, we can do maintenance before anything fails. We can order components before anything fails. So, it can help us make real time decisions. It can also help us with operational technology infrastructure. Okay. So, it can help us with asset performance management. You can manage the performance of the asset with time and you can optimize its operations. So, it can help us to asset performance management and operations optimization. So, that again can help us with time sensitive decisions that can impact the bottom line of our company. The other thing that you can do with digital twins is fleet management. You can manage an entire fleet of machines, entire fleet of trucks, entire fleet of machine tools. Okay. And it can also provide inputs to next generation designs of the next generation systems. So, fleet management is managing an entire fleet of the same type of systems. So, let us say UPS. Okay, UPS has these trucks that go out, they collect parcels and deliver parcels. Okay, so fleet of trucks. Okay, the same system that is in multiples. So, that creates a fleet. So, how to manage 10,000 trucks that are spread all over different cities in the United States. Okay, so managing the entire fleet. So, using digital copies of each if you had a digital copy of each truck, then you can manage them in real time, because you can create a map of where they are. Just like imagine so if you consider your Uber app showing all the different Uber taxis in the city, right. So, that is a fleet of Uber taxis, and you want to manage them so that they can get to the right customer in the least amount of time, right. So, when you go on your smartphone app and you order a Uber taxi, what they are doing is fleet management, because they have a twin of all the taxis that is available. That is why they are able to manage the fleet. So, good question. So, again all of these capabilities enable us to process big data. So, imagine how many Uber taxis are there in the country. So, that is generating a ton of data. So, that is big data. So, by having a digital twin, you are also able to process this big data and use it to your advantage. Okay, so, everyone gets why we should have digital twins, and you are also getting that we already have these digital twins in operation, and you are also using these digital twins, right. Good. So, what we can create with digital twins is a smart connected system topology. So, that example that I told you about the Uber app, that is a smart connected system, and its topology is visible to you immediately on your smartphone, right. So, digital twins are helpful in creating these smart assets, okay, edge systems, operational technology infrastructure, and IT systems. So, all of these are integrated to create your digital twins, and these are the benefits that you get: anomaly detection, predictive maintenance, asset performance management, operations optimization, and fleet management, and giving inputs to your next generation design. Okay. So, digital twins are used in a variety of applications, and they can be executed on the smart asset at the edge or on the IT or OT layers, depending on the response time that the application requires. Okay. So, digital twins help you do predictive maintenance by carrying out real time or time sensitive decisions. And when you implement the multiple digital twins for different applications, you can deploy each one differently into the system topology. So, if you create multiple digital twins for different applications, so you may create a digital twin for anomaly detection, you may create a different digital twin of the same system for predictive maintenance, another digital twin for asset performance management. So, what you can then do, you can deploy each one differently onto the system topology. Okay, so, you can deploy each digital twin differently. So, some example use cases is to optimize the maintenance schedules by using remaining useful life estimation. So, remaining useful life estimation is a key concept in digital twins, RUL, remaining useful life, how much useful life is there in the system, being able to tell that. Okay. So, this fan has operated for 1000 hours, it will operate another 500 hours, being able to tell that. Previously, we could not do that, but now we can if we create a digital twin of this fan. Okay. To optimize current operations, you can use simulation to create future what if scenarios. So, if you want to optimize your current operations, you can use this simulation in the digital twins to create future what if scenarios. Okay. So, you have your shop floor running, okay, but you want to derive more benefits, you want to reduce the operational costs of your shop floor. Okay. So, one way to do it is to create scenarios, create what if this happens, what if that happens, what if we have a flood, what if the cost of electricity goes up by 10 rupees per unit per kilowatt hour. Okay. So, you can create these what if scenarios and see what happens, okay, and that can help you optimize your current operations. So, let us look at some specific digital twin applications. So, we are talking about predictive maintenance. Okay. So, here is an example of a Baker Hughes predictive maintenance alarm system. So, in industrial automation and machinery applications, you can use digital twin models to determine the remaining useful life and the most opportune time to service or replace equipment. Okay. So, in normal operation, this system is showing this kind of characteristic. Okay. And then if you monitor closely with time, you see it is showing some deviations. Okay. So, after this yellow, now you see some of this green appear, and then it shows a lot of deviations. Okay. So, that is when you realize that maintenance is needed. Okay. And then you can create an alarm. Okay. So, digital twin can help you create these early alarms, so that you do not have to operate the machine at a lower level for a long period of time. You get the alarm early, so you order the components early, and therefore, you are able to optimize your system. The next application is that of operations optimization. So, you can create these sorts of Monte Carlo simulations to evaluate what is the potential asset behavior. You can use Monte Carlo simulations to evaluate what is the potential asset behavior based on the current state. So, you can use variables such as weather, fleet size, energy costs, or performance factors to trigger hundreds or thousands of what if simulations. Because you have a copy of the physical object on the computer that is continuously being updated, you can create lots of simulations based on various variables, okay, and that can help you evaluate the readiness. How ready are we for these disasters or these changes that might occur? And that can help you make adjustments to current system set points. Where should we operate? Okay. So, these simulations will tell you, okay, if we operate at 25 degrees Celsius, then this is what is going to happen. It will fail after 5,000 cycles. But if you operate at 20 degrees at a low temperature, maybe it will operate for 5,500 cycles. So, these sorts of insights can be got from the simulations based on the latest current state. So, you can feed in the current state, because the digital twin model has the current state, you can create the simulations based on the latest state of the machine. Whereas, typically conventional models used to be based on an ideal machine state, not on the current machine state. Okay. Because you have the digital twin, you can take the current machine state, this is where we are currently, and based on that, what is going to happen. And you can create many different scenarios, and you can evaluate whether you are ready or whether you may need to make any adjustment to the current system set points. So, that helps you optimize your system's operations, it helps you mitigate risk, your risk in your operations reduces, and you can reduce your cost, and you can gain system efficiencies. You can make your entire shop floor, or you can make your entire plant efficient. So, several benefits accrue from digital twins. One is that you get a complete history of your asset. So, not only it is giving you the latest state, but it is also keeping a record of everything that has happened with that component or that system right from the time it was operationalized. you get the full asset history. You are able to take proactive maintenance strategies, and you are able to simulate future scenarios. So, let us look at asset history in detail. So, this is the current state, okay, from machine startup, and then it captures all of the history that comes in. So, a digital twin is updated periodically to represent the real asset's current state, and over time these past states become the asset's history. Okay. So, all the current states are stored. Okay. So, this type of information, the type of information included in the history may differ based on how you are using the digital twin and what is captured in the current state. Okay. So, you can use digital twins in many different ways. So, depending on how you use it, the type of information may differ. Are you using it for predictive maintenance? Are you using it for some what if simulations? So, based on what you are using it for, the asset history will be different. Okay. So, for example, if you are using the digital twin for fault classification, the history captured by each digital twin can be the operational data from a specific, let us say, pump and its healthy and faulty state. Okay. Some pump characteristics and its healthy and fault state. We will see an example of a pump in the coming slides. Okay. In the future, you can compare the operational data from one pump to the digital twin histories of other pumps to understand how they behaved under similar faults and the effect on the fleet's efficiency. So, all of this data that you are collecting from one pump can be compared to digital twin histories from other pumps. Okay. So, many different pumps in your firm, and you have got separate asset histories for each pump, and then you can compare. Okay. Maybe this fan fails after 5,000 cycles, this failed after 5,200 cycles. So, you can make some comparisons, and that can give you some average usable life for each fan. Okay. So, that then tells you, okay, I need to plan a replacement in 2 years time, 3 years time, 4 years time, okay, on an average. So, that kind of useful information can be had from a detailed asset history. So, the next is of course having these proactive maintenance strategies. So, you can monitor the whole fleet and you can plan operational events and improve your maintenance strategies. So, previously maintenance which used to be ad hoc, now that maintenance is informed by the current state of the physical asset. So, why is this advantageous? So, imagine a situation in which one of the pumps is expected to fail soon. In that case, using your digital twin, you can assess how this will affect the efficiency of the fleet and what it will cost you. So, in the past, consider this as a scenario A, you had to order parts and run the pump in a suboptimal state until they arrive. Okay. So, you see, so you run this, okay, in the suboptimal state, okay, carry out some maintenance, and then maybe it fails here, you get it before that, but you have this suboptimal state of operation. Okay. So, when the parts are ordered and they are coming, you are running in a suboptimal state. But now, what you can do is, you can order replacements in advance and you can carry out your maintenance early as well. So, you can spend more to expedite your shipping to get the parts quickly, and you can reduce the time spent running suboptimally. You do not have this suboptimal state thanks to a digital twin. So, what does suboptimal state mean? So, that means let us say you have a CNC milling machine and you used to make 200 parts a day, but in the suboptimal state you may be making only 100 parts a day, because you are afraid that it will fail, because if it fails, then you are making 0 parts a day. Okay. So, you have seen some noise in the CNC milling machine, and based on that you are running at a lower productivity. But now, because you have the digital twin, you can order replacements in advance and you do not have this suboptimal state, or you reduce that suboptimal state. Make sense? So, the third benefit is simulating these future scenarios. So, you can simulate hundreds of future scenarios to see how factors such as weather, fleet size and different operating conditions affect the performance. So, you can create all of these sorts of simulations. So, you can create all these sorts of simulations and you can inform your maintenance staff about the expected failures in advance, so they can plan for future repairs and replacements. So, how does a digital twin work? So, let us look at a case study. So, imagine that your company has well sites. So, yours is a oil and gas company, it has a lot of different oil wells and they are at different locations from where you operate multiple pumps to extract oil and gas from the ground. Okay. So, as you will recollect from our discussion earlier today, a digital twin is an up-to-date representation of a real asset in operation. So, it could be the valve of this pump that is used to pump out the oil from the ground. Okay. It could be the pump itself or it could be many different pumps, well site with many different pumps. So, you can create digital twin for all of these. So, once you are given a digital twin project, then you would have to ask yourself, am I going to create a twin of the component? Am I going to create a twin of the system, or am I going to create a twin of the system of systems? Okay. So, when you are asked to create a digital twin, ask yourself that question, what is it that I want to monitor? So, these pumps may be located in many different places. Okay. So, you have chosen pump as your asset and let us say there are 3 well sites at different locations with multiple pumps running at each of the well sites. So, let us say you are Shell and you have got three sites where you are drilling and getting oil out, okay, and your pumps look at each of these well sites. So, what you can create is you can create an up-to-date representation of the pump by building a model that gets updated with the incoming data from the pump, such as data transmitted from sensors and different operating conditions. So, a digital twin model represents the current state of the pump. So, sensor measurements and operating conditions are sent from the pump to the model, from the pump to the model, the sensor measurements and the operating conditions, and that is used to update the state of the pump. Everyone follows? Yeah. So, this pump has some sensors and the sensor data is collected, okay, it is sent to this digital twin model and that tells you the state of the pump. So, once you have done that, your digital twin is ready. So, what will it help you with? So, it will help you with reducing the downtime of your equipment, it will help you with managing your inventory and it will help you with managing your entire fleet of pumps with what if simulations and operational planning. So, each pump contains expensive parts such as valves, seals and plungers. Okay. So, you have to identify what are the parts of the pump that are important that you want to maintain. Okay. You can prevent the failures of these parts by predicting them in advance, which will help reduce your downtime. You may also want to identify faults that develop and get insights into what parts may need repair or replacement. Okay. So, what will that do? That will help you manage your parts inventory. Okay. So, previously if you had a stockpile of inventory at each site, which was just random, 10,000 valves, it was just random. Okay. But now you can actually manage it more intelligently, because you have the real time data that is informing you, how many do I need. Okay. So, you can do better forecasting and that will help you manage your inventory better. So, in the 3 well site locations, all the pumps may have similar functionality. Okay. They might even be produced by the same manufacturer, but different operating conditions such as environmental temperature will affect how efficiently these pumps work. So, maybe this is located up north, this is located slightly down south. So, you have a pump here operating at maybe 30 degrees and you have a pump here operating at 10 degrees. Okay. So, because they are operating at different temperatures, that will determine how efficiently this works and this works. Maybe this operates at 90% efficiency and these operate at 75% efficiency. So, you can monitor the whole fleet and you can simulate future scenarios and you can make comparisons, and that will improve the overall efficiency of the fleet. Okay. So, Shell may have many different sites all over the world and they have sent the same pump everywhere, but they are operating at different temperatures. So, because you have digital twin which captures the real time data from all of these pumps, over a period of time you will be able to tell at what temperature regime my pumps are working better, what temperature regimes are actually helping them operate more efficiently and longer. Okay. So, that sort of information you can get by using the digital twin. Okay. So, you can carry out these what if simulations and you can improve your operational planning. So, to be able to, so this is all warm up about digital twins. Now, let us get into some details. Okay. So, you need to master these modeling methods. Okay. Now, modeling methods can be of different types. You can have data driven modeling or you can have physics based modeling. Okay. In data driven modeling, you collect a lot of data and that data is passed through some kind of machine learning interface. Okay. So, machine learning software, and that machine learning software has, so this is this what you are seeing here is a neural net. So, in a neural net, so there are these nodes, okay, and these are the arcs that are connecting the nodes, and these have weights, okay, and these weights are getting updated, they are getting tuned as you are getting more data. So, this neural net serves as a predictive model which is giving you these outputs based on the inputs. Okay, so, an example of that could be, let us say an electro discharge machine, okay, an EDM. In an electro discharge machine, you have many different operating parameters such as the pulse width, okay, the current value, okay, or the electrode material. So, those are the inputs, and based on those inputs you get an output which is the material removal rate, let us say. So, what is my material removal rate at 10 amperes? What is my material removal rate with 25 microseconds of pulse width? Okay. So, that output can be determined by having a model which is based on a network of neurons. This network of neurons is predicting what will be my material removal rate. So, what is that then? So, this network of neurons is the model of the system which is telling you what is the output based on my inputs. Okay. So, this model is updated with time based on the outputs that you are seeing for various input levels. So, it is based on data. There is no analytical model, there is no equation that is giving you the material removal rate based on the input parameters. It is just a model which is based on neurons. So, that is known as data driven modeling. Okay. On the other hand, you can have physics based modeling where you can create analytical models from scratch. You write out your differential equations and based on that you can predict your material removal rate. So, that is also possible. So, that is known as physics based modeling. So, physics based modeling can be carried out these days very nicely in MATLAB and its toolboxes such as SimScape. And equally you can also do that in MATLAB using neural nets like this. Okay, so, everyone understands the difference between data driven modeling and physics based modeling. Physics based modeling is based on the physics, okay, understanding the physics. So, based on the current and the pulse width, maybe you can model what will be the temperature distribution in the workpiece. Okay. So, once you model the temperature distribution in the workpiece, then you can tell, okay, this much zone of the workpiece will be above the melting point. So, that will be removed. So, based on that you can find out what is the material removal, right, and based on what is the pulse width, then you can find out what is the rate at which the material is getting removed. So, that is physics based modeling. Okay. Whereas, in data driven modeling, you do not know the physics, you do not try to figure out the physics, you just use a neural net and you feed it with lots of data and that gives you output. So, both of these types of modeling are applicable for digital twins. Okay. So, let us look at each one of them. So, firstly data driven modeling. So, let us say you want to optimize your maintenance schedules by estimating your remaining useful life. So, you use a data driven model. Your knowledge on the type of data from the pump will determine which model you will be using. Okay. So, there are different types of data driven models. We will see different types. So, if you have complete histories from similar machines, then you can use similarity models. Okay. So, let us say you have histories from many different pumps, then you can use what is known as similarity model. So, based on what similar machines have been doing, you can do a prediction for your current pump. So, that is known as similarity modeling. If you have data only from the time of failure, when different pumps have failed, then you can use survival models, how long different pumps have survived, but not their entire history. The entire history will have more details, like the temperature regimes during every single day they were in operation, okay, what were the flow rates inside them, etc., etc. So, you can have similarity models or you can have survival models. Okay. And the third type of model that you can make use of in calculating a remaining useful life is degradation models. Okay. So, if you do not have failure data, but you know there is a safety threshold, then you can use a degradation model. Okay. Let us say the flow rate is 10 meters per second, okay. But you know that when the flow rate is less than 9.5, then that means the pump is not working that well. Okay. So, that is your safety threshold. Below 9.5, we know that the pump is not working very well. So, that is the safety threshold. Okay. So, you may not have failure data, but you have a safety threshold, then you can use a degradation model. Okay. Everyone understands? So, three different types of models: similarity models. Okay. So, where you have detailed data over the entire lifespan of the pump from many different pumps. Okay. The survival model, where you know when it fails, and the degradation model, where you know the safety threshold. Okay. So, everyone understands? So, there were many key points in this video. So, if you look here,
so in the pre-processing step,
so here you can see, here there is sensor data from 15 sensors, right? But not all of the sensor data is useful. So, this sensor here, you see its value changes with time. Okay. So, if you draw a mean through these data points, it goes up like that, and when it reaches here, that is when the system fails, right. So, likewise you can see that for this one, okay, but you can't get any trend from this one, the values remain almost the same, can't get any trend for this one. So, not all of the sensor data is helping you do the prediction of the failure, right. Only some of the sensors are critical. So, this pre-process data step is quite crucial. So, you need to pre-process and see which sensors are actually giving you a good indication of failure of the system and which are not. So, filtering the non-essential ones out is a crucial step. So, acquiring data is important, but then how you process the data is crucial to how efficiently your digital twin works. Okay. So, to do that, what you need to do is identify which of the sensors are actually going to give you a good indication of the condition of your physical asset. So, you have to identify the condition indicators, and again for each one of the steps there are a lot of mathematical methods available. Okay. So, once you have identified that, then you need to do what is known as model training. You need to train your model. So, another crucial part of this video was where the speaker was talking about reducing this gap. Okay. So, there is a predicted failure time and there is an actual failure time. So, with time, as you get more and more data from all your physical objects, this gap reduces, okay, and the accuracy of your prediction model improves. So, it is not only important to collect data, but it is also important to then do all of the work after that, pre-processing it, okay, then choosing which will give you the condition indicators, and then once you have done that, improving the accuracy of your model with time, okay, and that is where the value lies, okay. So, remaining useful life, let us look at it in more detail. The length of time that the machine will operate before it requires repair or replacement, that is remaining useful life, okay. By estimating this, engineers can schedule maintenance, optimize your operating efficiency and avoid your unplanned downtime. So, therefore, estimating RUL is a top priority in predictive maintenance programs, and the RUL estimation model provides you a confidence bound RUL prediction. What does it mean? So, it will give you some bounds, remaining useful life, let us say 1000 cycles plus minus 20 or plus 20 minus 30, okay. It will give you a prediction with some confidence bounds. The model inputs are the condition indicators or the features extracted from the sensor data whose behavior changes in a predictable way as the system degrades. Okay. So, you extract the features from the sensor data. Now, which RUL model you must use? So, it depends on what data is available. So, is it the lifetime data indicating how long it took for similar machines to reach failure, or is it the run to failure histories of similar machines, or do you know the threshold values of the condition indicators that detects the failures? Okay. So, the three different models. So, let us look at the survival model. So, to create your survival models, you can use what are known as proportional hazard models and probability distributions of component failure times. Okay. How many of you have done a course on probability and statistics at IIT? I mean at university, okay. Some of you have not done, you did not have maths 2 in your undergraduate, you had only maths 1 or you did not have any probability and statistics separate course, okay. I am just asking so I can pitch it right for everyone, okay. So, if you have done a probability and statistics, then we can talk about talk at a slightly higher level. If you have not done, then you will have to learn the basics, okay. So, survival model uses probability distributions of component failure times, okay. So, simple example is estimating the discharge time of a battery based on past discharge times and covariates such as environmental temperature and load. So, the battery may be operating at a certain environmental temperature and certain load, okay. So, depending on that, how quickly does the battery discharge. So, you can create this survival function plot, okay. And let us say you want to know after 75 cycles what is the probability that this battery has reached its end of operation, okay. So, you can get it from this sort of a plot. So, the probability that a battery will fail is based on how long it has been in operation, okay. This plot shows that if the battery has been in operation for 75 cycles, there is a 90% chance, okay, because this intersects with 0.1, that it is at the end of its lifetime. Now, let us look at similarity models. So, if you have a database of run to failure data from similar components or different components showing similar behavior, okay. So, many different components or different components showing similar behavior, you can use similarity methods. So, these methods capture degradation profiles and compare them with new data coming in from the machine to determine which profile the data matches most closely. So, let us say many different machines, you have collected lots of data over time and you have plotted this condition indicator values against the lifetime variables or the cycles of operation. So, this is all the data that you have got from past histories, and your current history is this deep line in red, okay, and this is where you are currently operating, and these are the failure events, okay, that you have captured and that is indicated with the star. Okay. So, based on this, you can say that the remaining useful life when the machine is here is another around 65 cycles. Okay. Another 65 cycles, because it will go on this trajectory. So, between here, if you draw the ordinate here and if you draw it here, then this length here is around 65. Make sense? Yeah. So, that is how you use the model. The degradation model. Okay. So, degradation model is particularly useful when you have a conservative maintenance schedule. Okay. So, that means machines rarely fail. So, you have a maintenance schedule that is really conservative. That means you really try to avoid failure at all costs. So, you do a lot of maintenance. Okay. So, this means run to failure data or lifetime data is not available. You replace the tools before it fails. You do not have any failure data, because none of the tools fails, because before it fails, long before that, you just do your maintenance. So, you may have information on prescribed threshold values. So, in that case, you are replacing your tools when it crosses a certain threshold. So, you may have data on threshold values. So, for example, the temperature of liquid in a pump cannot exceed 75 degrees Celsius, and the pressure must be under 155 bars. So, with this threshold information, you can fit degradation models to condition indicators extracted from the sensor data, which can linearly change linearly or exponentially with time. So, these models will then estimate your RUL by predicting when the condition indicators will cross the threshold. Okay. So, you can use them with a fused condition indicator that incorporates information from more than one sensor. So, your condition indicator can be a weighted average of one or more sensor readings. Okay. So, you do not have to have a single condition indicator, you can have a single condition indicator, but it is based on multi-sensory data, weighted average for instance. And you can use techniques such as principal component analysis. So, here is an example. Okay. So, the remaining useful life prediction. Okay. So, this is for a high speed bearing in a wind turbine. So, based on the current data which is in blue, okay, based on this current data, you do a fitting, and that fitting gives you this kind of a bound, okay, two curves, and so based on that you come up with this intermediate mean curve, and that mean curve meets the failure threshold here. So, that means between this and this there is 9.5 days. So, this bearing has an estimated remaining useful life. So, between this and when it fails, so this is 49.5. So, 49.5 minus 40 gives you 9.5, because currently we are here. Everyone follows? So, this degradation model is one that evolves with time, you see. So, this should run, it's a video. So, you see, depending on how your sensor data is changing, your inner and outer control limits are changing. Okay. So, these estimates of where this system will go changes, and based on that your RUL also prediction also keeps changing. So, in red is your degradation model. So, this is your confidence interval. Okay. This is your current health indicator of the system, okay, and this is your threshold. So, we now turn our attention to physics based modeling methods. So, in physics based modeling methods, you create these sorts of models based on the physics. Okay. So, you have all of the, so you have models of your system, okay, with these analytical models, and that is getting fed with the data. Okay. So, input data, output data, etc. So, this is an example of a physics based model by connecting mechanical and hydraulic components. So, this model is fed with data from the pump, and its parameters are estimated and tuned with the incoming data to keep the model up to date. Okay. So, this is a physics based model. So, using this model you can inject different types of faults and simulate the pump's behavior under different fault conditions. So, once you have a physics based model, you can actually simulate all different kinds of faults. So, you can change some of these values, make them faulty and see what happens to the output values. So, how will the pump behave? Okay. So, physics based models are also very useful, and those can also be created in software tools such as MATLAB. You can use filters. Okay. So, this is an example of how to use Kalman filters. How many of you have heard of Kalman filters? One. Okay. So, it is from advanced controls theory, digital signal processing. Okay. So, the pump may have some noisy measurement data, and because the measurement data is noisy, we put it through a filter. It is known as a Kalman filter, and that gives you a better estimate of the state of your physical object. So, often the measurement data that you collect may have a lot of noise in it, and in that case it is useful to use a filter such as a Kalman filter. So, Kalman filter can be used as a digital twin. It can model the degradation of the pump as a state and periodically update the state to represent the current state of the pump. Okay. So, the key question is, well, so we have learnt all the different techniques of digital twin modeling. How many digital twin models do you need to create? So, it depends on the intended use. Do you want to do RUL estimation? So, create a twin for it. Do you want to do fault classification? Create another twin for it. Okay. So, for every individual asset you need to create a unique digital twin. This means that for each of the pumps at different well sites you need to create a unique digital twin that has been initialized with the specific pump's parameters. Okay. So, you need to initialize your pump. Then the total number of unique twins you need depend on the number of applications. So, if you are modeling a system of systems, you may or may not need a twin for each system of components depending on your required level of precision. Okay. So, you may be told by a company, okay, out of 100 pumps, if we have 10 pumps data, that gives us an overall indication of how our site is running. So, depending on the level of precision and how much money you can invest, etc., so you can create twins of different fidelities. Okay. So, where are digital twins taking us? So, currently there is a lot of research in this, and that is why I encourage you to take your time to understand this topic well, because there is a lot of potential and there are a lot of jobs in this area, and also there is a lot of research going on. Okay. So, it is about incorporating real time data flows, which is not easy. Okay. You need good bandwidth, you need all this high fidelity sensors, you need to be able to process the sensor data properly, you need all these statistical tools of finding out which are the right ones for condition indication, etc. Okay. So, you need to incorporate right time or real time data flows. There is a lot of research into how to use AI and ML. How to make these digital twins autonomous, so they can self build themselves. Can they be federated? So, can we make digital twins federated and controlled by central authorities? How can we make them of high fidelity, so that they are secure and they are operated in a sustainable manner? Okay. So, many different research topics, and there is a lot of potential in this field. There are a lot of jobs in this field. Okay. To summarize, a digital twin is an up-to-date representation of an actual physical asset in operation. Digital twins are characterized by two-way flow of information between the asset and the model. Okay. So, that is what distinguishes them from digital shadows and digital models. There are three key benefits of digital twins, which are in tracking the asset history. You can track the history of your asset, you can carry out maintenance in a proactive manner, and you can simulate future scenarios. And you can do RUL modeling to build your digital twins. And we also learnt about 3 types of RUL estimators, which are similarity models, survival models and degradation models. Okay. Thanks everyone for coming, and I'll see you all in the next class.